I wanted to tell you about the most important equation in physics, not E equals mc squared, not Schrodinger's equation, not Maxwell's equations, the most important one. The one that holds everything together. Every conservation law, every symmetry, every reason the universe has rules instead of chaos. And I want you to try something. Try to picture the person who wrote it. You're seeing a man, aren't you? Probably old. Probably with wild hair and a chalkboard. Here's the thing. You're wrong on every count. It was a woman. Her name was Emmy Noether. And unless you studied graduate-level physics, you have almost certainly never heard of her. That should bother you. It bothers me. And she's not the only one. See, I've been thinking about this for a long time. Who we remember and who we don't. And what I've found is something that genuinely disturbs me. The people whose names, you know, Einstein, Bohr, Heisenberg, even me. We're the visible part of the building, the facade, but the foundation, the load-bearing walls, the steel beams, the things that actually keep the structure from collapsing. Those were built by people whose names got lost, not because their work was minor, because the world wasn't ready to listen. I wanted to tell you about 4 of them. 4 people who changed everything, and I mean everything. The way we understand energy, atoms, heat, and the nature of reality itself. 4 people that textbooks barely mention, or mention only in passing, the way you mention the guy who poured the concrete for a cathedral, and I think by the time I'm done, you're going to be angry. Not at me, at history. Let's start with the equation I mentioned. Let me make this real for you. Hold your hand out in front of you. Go ahead. Actually do it. Now move it 6 inches to the left. Did anything change? Did the laws of physics shift? Did gravity get stronger? Did light slow down? No, nothing changed. The physics is the same here as it is 6 inches to the left. That seems obvious, trivially obvious. It's the kind of thing you'd never bother to say out loud. Emmy Noether proved that it's the most important thing in the universe. In 1918, while the First World War was still killing people, she published a theorem that said this: every symmetry of the laws of physics corresponds to a conservation law. Every one. You move through space and the physics doesn't change. That gives you conservation of momentum. The physics doesn't change over time. That gives you conservation of energy. You rotate and the physics stays the same. Conservation of angular momentum. These aren't separate discoveries. They're all the same discovery. They all come from Noether's theorem, one idea, and it generates the entire framework of conservation laws that every physicist on Earth uses every single day. Now, picture the thought experiment. Imagine you're on a perfectly smooth ice rink that stretches out in every direction. Infinite. No walls, no friction. You push a puck. It slides. It will slide forever in a straight line at the same speed. Why? Because every point on that ice is the same as every other point. There's nothing special about here versus there. The symmetry of the space demands that the puck's momentum be conserved. That's not just a convenient observation. It's a mathematical necessity. Noether proved that. She showed that symmetry isn't just pretty. It's the reason anything is conserved at all. They take away symmetry and conservation laws vanish. Energy isn't conserved anymore. Momentum isn't conserved. The universe becomes lawless. Every particle physicist working today uses her theorem, every single one. It's the backbone of the Standard Model. It's the reason we know what to look for when we smash particles together. It is, without exaggeration, the most important single theorem in all of physics. And here's what happened to the woman who proved it. She arrived at the University of Göttingen in 1915, invited by David Hilbert and Felix Klein, 2 of the most powerful mathematicians in the world. They needed her. They knew she was a genius, but the faculty refused to give her a position, not because of her work, because she was a woman. She couldn't lecture under her own name. For years, her courses were listed under Hilbert's name. Mathematical Physics Seminar, Professor Hilbert, with the assistance of Dr. Noether. She wasn't paid. She wasn't given a title. Hilbert fought for her. He stood up in a faculty meeting and said, and this is a real quote, "I do not see that the sex of the candidate is an argument against her admission as privatdozent. After all, we are a university, not a bathhouse." It didn't work, not for years. She eventually got a modest position, never a full professorship. Then the Nazis came, and because she was Jewish, she was thrown out in 1933. She fled to the United States, taught at Bryn Mawr College, and died 2 years later. She was 53. After she died, Einstein wrote a letter to the New York Times. He called her, and I want you to hear this carefully. the most significant creative mathematical genius thus far produced since the higher education of women began. Most people have never heard her name, but they've heard of every law her theorem explains. That's the kind of forgetting I'm talking about. And she's not the only one. Let me take you back further to a man who was right, provably, demonstrably, mathematically right, and it killed him. Ludwig Boltzmann believed in atoms. Now you hear that and you think, of course atoms are real. What's the controversy? But in the 1890s, this was a way off, not a polite academic disagreement, a war. The most powerful physicists and philosophers in Europe, Ernst Mach, Wilhelm Ostwald, said atoms were a fiction, a mathematical convenience. You couldn't see them, you couldn't touch them, you couldn't measure them directly. Mach in particular was brutal about it. He was a positivist. He believed science should deal only with what you can directly observe, and you couldn't observe an atom. So atoms to Mach were metaphysics, not science or fantasy. Boltzmann said, no, atoms are real, and I can prove it. Not by showing you one, but by showing you what happens when you do the math as if they're real. He built an entire framework, statistical mechanics, that explained heat, pressure, entropy, the behavior of gases, all of it by treating matter as being made of tiny, discrete, colliding particles. His equation, S equals K log W, connects the entropy of a system to the number of microscopic arrangements its atoms can take. It's one of the most beautiful and powerful equations ever written. And his colleagues told him he was deluding himself. Picture this, 1895, a scientific meeting in Lübeck, Germany. Boltzmann stands up to defend his work. Ostwald attacks him. Mach's followers attack him. The room is hostile. Boltzmann is not a natural fighter. He's a sensitive man, prone to depression, physically unwell. He defends his position with mathematics. They dismiss his mathematics. They say he's building castles on foundations that don't exist. The atoms he's calculating with, they're not real. He's doing elaborate, beautiful, meaningless arithmetic. Imagine knowing you're right, having the equations, having the predictions, and watching the most respected people in your field tell you to your face that you've wasted your life. Boltzmann fought this fight for over a decade. His depression deepened, his health deteriorated. On September 5th, 1906, while on a summer holiday in Duino, near Trieste, Einstein showed mathematically that this jiggling was exactly what you'd expect if water was made of tiny molecules colliding with these suspended particles. 2 years after Boltzmann's death, in 1908, the French physicist Jean Perrin ran the definitive experiments. He watched microscopic particles of gambosia, a kind of resin, suspended in water, tracked their movements with a microscope, and showed that their behavior matched Einstein's predictions with stunning precision. Perrin calculated Avogadro's number from those observations. He proved atoms were real. He won the Nobel Prize for it in 1926. Boltzmann was right about everything. His equation works. His framework is the foundation of modern thermodynamics and statistical mechanics. Every physicist alive uses it. He didn't live to see it. They carved his equation into his tombstone, S equals K log W. It sits there in the Zentralfriedhof in Vienna, a cemetery, not a lecture hall, as if to say, here lies the answer you refuse to hear. But that's not the strangest case, not by a long way. Now, I want to tell you about a man who might be the most invisible genius in the history of American science. His name is Josiah Willard Gibbs. Einstein called him the greatest mind in American history. Not the greatest physicist, not the greatest scientist, the greatest mind. And nobody knew who he was. Gibbs spent his entire career at Yale University. He never left New Haven, Connecticut. He was quiet. He was modest. He had no interest in publicity, no talent for self-promotion, and absolutely no instinct for making himself heard. He was the opposite of everything you need to be if you want the world to notice your work. And his work was extraordinary. Between 1876 and 1878, Gibbs published a paper called On the Equilibrium of Heterogeneous Substances. I say a paper. It was over 300 pages long, and it was, in effect, the founding document of chemical thermodynamics. It introduced the concept of chemical potential. It established the phase rule. It created the mathematical framework that describes how substances change from solid to liquid to gas, how chemical reactions reach equilibrium, how mixtures behave. Every chemist and every chemical engineer in the world today uses ideas that Gibbs put into that paper. He also, almost incidentally, invented vector calculus as a practical tool. and coined the term statistical mechanics of our. Now, here's the thought experiment. Imagine you're trying to describe the state of a cup of water, not just its temperature, everything about it, every possible thermodynamic variable. You'd need a surface, a mathematical surface in a space where every point represents a different combination of energy, entropy, and volume. Gibbs saw this surface. He described it. He mapped its geometry. He showed that the curves and ridges and valleys on that surface correspond to real physical phenomena. Boiling points, freezing points, critical points where the distinction between liquid and gas disappears entirely. It's an abstract idea, but James Clerk Maxwell, the man who unified electricity and magnetism, read Gibbs's paper and was so moved by it that he built a physical plaster model of that thermodynamic surface with his own hand. Maxwell sculpted it, painted it, and sent a cast of it across the Atlantic to Gibbs at Yale. That model still exists. You can see it at Yale to this day. Here's the problem. Gibbs published all of this in the Transactions of the Connecticut Academy of Arts and Sciences. You've never heard of that journal. Nobody had heard of it then either. It had almost no readership, almost no distribution, and absolutely no profile in the European scientific community where the real conversations were happening. Gibbs might as well have carved his equations into a rock and dropped it in the ocean. Maxwell found it. Maxwell recognized it. Maxwell championed it. But Maxwell died in 1879 at the age of 48. And after Maxwell died, there was a saying. It circulated at Yale, half joke, half tragedy. Only one man lived who could understand Gibbs's papers. That was Maxwell, and now he is dead. Gibbs kept working. He kept publishing in the same obscure journal. He kept teaching at Yale. For the first 10 years without a salary, he didn't seem to mind. He just wanted to do the work. He died in 1903. He was 64. It took decades for the world to catch up to what he had done. Einstein knew, the people who knew. But the public never learned his name. He's the architect of a building that everyone uses and nobody tours. And then there's one more. And this one might be the most painful of all. Hugh Everett III was a graduate student at Princeton in the 1950s. His advisor was John Wheeler, one of the greatest physicists of the 20th century, a man I knew well. Everett was brilliant, quiet, stubborn, mathematically ferocious, and he had an idea that was either insane or the most important insight in quantum mechanics since the wave function itself. Here's the problem he was trying to solve. In quantum mechanics, a particle exists in a superposition. It's in multiple states at once. When you measure it, you get one result. The particle collapses into a definite state. That's what the Copenhagen interpretation says. But Everett asked a question that nobody wanted to hear. What causes the collapse? Where does the rest of the wave function go? What makes measurement special? And his answer was nothing. Nothing is special about measurement. There is no collapse. When you measure a particle, the universe doesn't choose one outcome. Every outcome happens. The universe splits. You in one branch see the particle spin up. You in another branch see it spin down. Both are real. Both continue. Neither knows the other exists. This is the many worlds interpretation, and it sounds insane. I know how that sounds. Believe me, I know. But here's the thing. The mathematics is clean. Everett didn't add anything to quantum mechanics. He subtracted. He took away the collapse postulate, the one part of the theory that had always been ad hoc, always been tacked on, never been derived from anything deeper, and showed that the rest of the equations left alone naturally produced the appearance of collapse. The branching isn't something he invented. It's something the equations already do if you don't artificially stop them. Wheeler thought it was important. He helped Everett shape the thesis, but he also knew it would be explosive. He made Everett cut the original thesis, which was titled Wave Mechanics Without Probability, down to a shorter, less provocative version. Wheeler was trying to protect both Everett and the idea, and he wanted Everett to go to Copenhagen to present the work to Niels Bohr himself. In 1959, Everett went. He sat with Bohr, and Bohr dismissed him. Not violently. Bohr was never violent, but completely. Bohr didn't engage with the argument. He didn't address the mathematics. He simply refused to accept that there was a problem with the Copenhagen interpretation that needed solving. The conversation went nowhere. Everett left Copenhagen knowing that the most powerful figure in quantum physics had closed the door. He never published another physics paper. He left academia entirely. He went into defense analysis, operations research, nuclear weapons strategy, computer modeling. He drank heavily. He gained weight. He stopped talking about physics. On July 19th, 1982, his 18-year-old son, a kid named Mark Oliver Everett, who would later become the frontman of a band called Eels, found him dead in bed. Heart attack. He was 51 years old. Everett had told his wife he wanted his ashes thrown in the trash. She kept them in a filing cabinet for years before honoring the request. Now, today, the many worlds interpretation is one of the leading frameworks in quantum mechanics. It's taken seriously by a significant fraction of working physicists. Sean Carroll champions it. David Deutsch builds on it, the decoherence program. The most important development in quantum foundations in the last 50 years is essentially the mathematical vindication of what Everett was trying to say in 1957. He was right. Or at the very least, he was far more right than anyone in his lifetime was willing to admit. He died thinking his work didn't matter. You're thinking, okay, these are sad stories, but maybe they were forgotten for a reason. Maybe the work wasn't recognized because it wasn't ready or wasn't clear or wasn't presented well enough. Maybe history doesn't owe anyone recognition. Maybe the work speaks for itself eventually, and that's enough. And you're not wrong to think that. There's something to it. Gibbs did publish in an obscure journal. Boltzmann was difficult to follow. Noether's work was abstract. Everett's idea was radical. But here's where that breaks down. The people who got famous, who got the credit, the textbook chapters, the Nobel Prizes, they weren't always clearer. They weren't always more rigorous. They weren't always more right. They were often just louder or luckier. Or they happened to be men at a time when that mattered. Or they happened to be in the right country. Or they happened not to challenge the person who controlled the field's orthodoxy. Noether's work was as clear as mathematics gets. The faculty at Göttingen didn't reject her ideas. They rejected her because she was a woman. Boltzmann's mathematics was rigorous and correct. His opponents weren't offering better math. They were offering a philosophical preference for not believing in things they couldn't see. Gibbs's work was so good that the greatest physicist in the world built a sculpture of it with his bare hands, and Everett's math was never refuted. It was ignored. That's not the work failing, that's the system failing, and that distinction matters. Because if history forgets people based not on the quality of their ideas, but on the circumstances of their lives, their gender, their temperament, their willingness to fight, their location, their luck, then what we call the history of physics isn't really history. It's a highlight reel, and highlight reels lie. So what do we do with this? Well, I'll tell you what I think. I think physics doesn't care about any of it. The equations don't know who wrote them. Noether's theorem works whether you know her name or not. Boltzmann's constant shows up in every thermodynamic calculation on Earth, and the atoms he believed in don't care that Ernst Mach didn't believe in them. Gibbs's chemical potential governs every reaction in your body, right now, every enzyme, every ion channel, every breath. And it does this without asking whether you've read his paper. Everett's branches, if they exist, don't need your permission. The physics doesn't care. But we should, because these aren't just stories about the past. They're about the present, right now. Today, there are people working on ideas that the mainstream doesn't take seriously, ideas that might be wrong, but ideas that might also be the next Noether's theorem, the next statistical mechanics, the next many worlds interpretation, and some of those people will be ignored, not because their work is bad, but because the system isn't built to listen. Here's what I still can't quite settle in my own mind, and I want to know if it bothers you too. Is this a fixable problem, or is it just the nature of how science works? Does every generation have to lose some of its best ideas to neglect and prejudice and bad luck and only recognize them decades later? Or could we build a system by peer review, funding, institutional culture that catches these people before they're destroyed by the process? Boltzmann didn't have to die. Noether didn't have to teach for free. Everett didn't have to throw away his career. Those weren't inevitable outcomes. They were choices made by institutions, by individuals, by a culture that valued conformity over truth. And I think we owe it to them and to the people working right now to ask whether we've actually fixed any of that or whether we're still making the same mistakes with different names. There's another piece to this. What happens when the person who gets forgotten isn't just a physicist, but an entire tradition of thinking and a whole way of approaching nature that got sidelined for a century? And I think that deserves its own conversation. But for now, I want to leave you with this. Somewhere in Vienna, in a cemetery full of composers and emperors, there's a tombstone with an equation on it, carved in stone by people who finally understood what it meant. And the man who wrote it isn't there to see it, because the world's refusal to listen was louder than the truth, and he believed them instead of the math.